We're going to look at what momentum means in the context of conservation of momentum. It's not necessarily something that's generally true, but if you have a closed system, so there's no mass flowing in and out of your system, and the system is also isolated, so the net external force on the system vanishes, then the vector for the total momentum of the system is going to remain constant. So delta P is zero, so P final equals P initial. We need to remember that that is a vector statement. So it holds along possibly each of the three spatial coordinate directions. There's also the possibility that you could have a system that's isolated along one axis, but is not isolated along a different axis because, say, for example, gravity is acting along that additional axis. So keep that in mind. Then go through some questions based on conservation of momentum. And I love these first few questions. I find them very illustrative. So we have rain falling vertically into an open train car that's rolling along a straight horizontal track with negligible friction. As a result of the accumulating water, the speed of the cart is going to increase, does not change, or decreases. So this is, I remember this one when I was in high school. The question has stuck with me since then. I think it's a fun head scratcher, and you wind up coming to an intellectually pleasing conclusion. So rain falls vertically into an open cart. The cart is rolling along a straight horizontal track with negligible friction. As a result of the accumulating water, what does the speed of the cart do? So think about it, talk it over with your neighbors, and then we will talk about the answer together here in just a second. All right. We come to the conclusion, based on our understanding of conservation momentum, that because the cart is isolated in the horizontal direction, it will slow down, which is just fun to say. So there is not a net force acting on the cart or the water left, right. So it's isolated along that direction. So its momentum is conserved along the horizontal direction. There is a force to stop the raindrops, but that acts vertically. And vertical has no projection on horizontal. So what you wind up saying is that the mass of this cart and its contents plus its speed is equal to some constant. And then obviously for an isolated system, as the mass is increasing, because it's isolated, mass increases, the speed is going to have to decrease. All right. There's a follow-up question to this. Try that next. All right. Rain falls vertically into an open cart rolling along a straight horizontal track with negligible friction. As a result of the accumulating water, the kinetic energy of the cart does it increase, stay the same, or decrease? So now we're asking not about the speed, but the kinetic energy. So think about what you think is going to happen and then talk it over with your physics friends. You can unpause the video and we'll go over the answer together. All right, so the kinetic energy is going to decrease, but let's see why. So if you're thinking, whoops, come back. You're thinking of kinetic energy as K equal to a half m v squared. Well, we know that the mass is decreasing. I'm sorry, the mass is increasing and the speed is decreasing. But then that doesn't really tell me what happens to the kinetic energy. A better way to formulate this is with our new best friend for this chapter, that I can write the kinetic energy as p squared over twice the mass. And then the momentum is constant. So the numerator stays fixed and the mass is increasing because water is falling into the cart. So the kinetic energy has to decrease. And so there it's clear what happens to the kinetic energy. Whereas in this form, I have one term that's getting bigger, I have another term that's getting smaller, and I don't really know which is which. This other formulation makes it clear. You could take these two questions and go into a tremendous amount of depth with them. Because if the rain is falling vertically when the train is going at one speed, right, then as the speed changes, unless uh, the velocity vector for the rain also changes, it's no longer going to be vertical. So you can do all sorts of things with these questions and get into different frames of reference, and it's a good launching point to think about physics, whether it's an isolated system or not. But for right now, we're just thinking about it in terms of conservation of momentum. All right. Let's try some more questions. All right, a little classic physics hypothetical. Get everyone in the world into one place, and we agree that on a prearranged signal, everyone is going to jump up while all the people are in the air. Does Earth gain momentum in the opposite direction? And there's 4 answers to that question. Read through them and see which one is correct. So there are 3 wrong answers and 1 right answer. So read through them all, think them through, think about conservation of momentum. And when you are satisfied that you've argued through the answer, you can unpause the video and we'll go over it together. All right, let's go through all the answers. So no is option 1. So that part's wrong. The inertial mass of the Earth is so large that the planet's change in motion is imperceptible. So that that phrase after the semicolon is perfect. That's good physics, but the preceding word no is incorrect. Option 2, yes. Because of its much larger inertial mass, however, the change in momentum of Earth is much less than that of all the jumping people. Well, then it can't conserve momentum. For momentum be conserved, the change in momentum of the people is equal and opposite to the change in momentum of the Earth. So if I truly have an isolated system and momentum is conserved, I can split it into 2 parts, and the change in momentum of one part has to be equal and opposite to the change in momentum of the second. It's like Newton's third law for momentum. So first word is great, but then the rest of it is off the rails. All right, option 3, which is the correct one. Yes, Earth recoils like a rifle firing a bullet with a change in momentum equal and opposite to that of the people. That is precisely correct. And then it does not depend. Newton's third law is not an opinion. You doesn't depend on anything. It just is. All right. Suppose the entire population of the world gathers in one spot, and at the sound of a prearranged single signal, everyone jumps up. About a second later, 8 billion people land back on the ground. After the people have landed, Earth's momentum is it the same or different? So which of those 2 statements is correct? Think about what you think the answer is, talk it over with your friends, and then unpause the video and let's see. All right, so Earth and all the people on it together as a system. There's some jumping, there's some moving, there's some blah, blah, blah. but all the people land back on the Earth. And so after all the people have landed, all the people are at rest relative to the Earth. Therefore, Earth's momentum has to be the same as it was before all the people jumped. If it was different than what it was before all the people jumped, then I would have changed the momentum of an isolated system, which there's not a way to do that.